Good morning, everyone. Yeah, we have already finished the chapter 20, and today we will start chapter 21, electric potential. Yeah, and okay, let's share my screen. Okay, yeah, today we will start learning chapter 21, electric potential. Actually, in chapter 20, we learned electric forces, electric charge, electric and some field, electric field. Yeah, and today we will deep more we will learn electric potential. Yeah, okay, let's begin. Yeah, this is this chapter's goal, to calculate and use the electric potential and electric potential energy. Yeah, so we will talk about what is electrical potential and what is electrical potential energy and how to calculate them and how to use them. Yeah, in our real life. Okay, let's continue. Yeah, before we talk about chapter 21, let us do some preview. Yeah, the first one we will talk about the electric potential. Yeah, the voltage of a battery is the difference in electric potential between its two terminals. You can see the batteries. Yeah, we usually use the batteries in our real life, and actually the voltage of a battery is the difference in electric potential between its two terminals. Yeah, because of the electric potential. Yeah, and then we can use the battery to get the power. Yeah, we will talk about more in this class. And you will learn how an electric potential is created when positive and negative charges are separated. Yeah, and then we will learn capacitors. Yeah, the capacitors on this circuit board. Yeah, these all are capacitors. Yeah, the capacitors on this circuit board store charge and electric potential energy. I don't know, if you have heard the capacitors or use the capacitors. Yeah, actually, it's a very useful electrical component. Yeah, the capacitors can store charge and electric potential energy. Yeah, and you will learn how energy stored in a capacitor depends on its charge. Yeah, and also, yeah, we will learn those two, mainly focus on those two things, and also let's look. Also, we will check some potential field for potential and field. Yeah, this is the other one we need to learn in this chapter. Yeah, there is an intimate connection between the electric potential and the electric field. Yeah, you will learn how to move back and forth between field and potential representations. Yeah, actually there are some intimate connection between electric potential and electrical field. Yeah, we have already learned the electric field. Yeah, for this positive charge. Yeah, the potential field, the electrical field is just like this, and the potential electrical potential is just like the green lines here, and yeah, we will learn how to move back and forth between field and potential representations in this chapter. Okay, and let's continue. And before we start this class, let's look back something. Let's look back work and potential energy. Yeah, in section 10.4, yeah, this you actually you have already learned in college physics 1. You learn that it is possible to store potential energy in a system of interacting objects. In this chapter, you will learn a new form of potential energy. Yeah, a new form of potential energy called electric potential energy. Yeah, this roller coaster is pulled to the top of the first hill by a chain. You can see here is a roller coaster is pulled to the top of the first hill by a chain. The tension in the chain does work on the coaster, increasing its gravitational potential energy. Yeah, this is like a, it's not like it's just an example like a potential energy, and for this image, it increases its gravitational potential energy. And in this chapter, we will learn like a electric potential energy. Okay. Yeah. Let's try to stop to think this question. Yeah. You lift a book at a constant speed. Yeah. Pay attention. This is a constant speed. Which means what? Which means the net force is zero. Yeah. Which statement is true about the work W done by your hand? The change in the book's gravitational potential energy, delta UG. Yeah, yeah. This is like a, yeah. Actually, you can see this is a constant speed, which means the net force is zero. Which means what like the work done by your hand actually it will equal the change in the book's gravitational potential energy. Yeah, and it should be greater because it is up, so it should be greater than zero. Yeah, and the answer should be C. That makes sense to you? Okay, and this is today's class goal. Yeah, firstly, we will understand electric potential energy and electric potential. Yeah, what is electric potential energy and what is electric potential? And then we will explore sources of electric potential. And then we will study electric potential and conservation of energy. And finally, we will learn how to calculate the electric potential. Okay, let's firstly, let's check like electrical potential energy and electrical potential. Yeah, here are some videos you can check. Yeah, you just click this link and you can open that. I will now play this in the class. Okay. Chapter 20 introduced a new force, the electric force. Actually, yeah, in this textbook, yeah, chapter 20, we just introduced a new force, the electric force. Electric force has an associated form of potential energy. Yeah, once we explore electric potential energy, we will introduce the related concept of electric potential. Yeah, you are already familiar with the concept of electric potential. You have used the word voltage before, am I right? Yeah. So like you yeah, after this class you will know how the voltage related to electric potential. Yeah, actually voltage is a mirror of electric potential. Yeah, amazing, am I right? Actually, you have already touched electric potential very early. Yeah, okay. Uh, Conservation of energy was a powerful tool for understanding the motion of mechanical systems. Yeah, yeah. I like conservation of energy. I think you have already learned this in college physics 1, like in chapter 10 or something. Yeah, and actually, yeah, this is a very useful tool for understanding the motion of mechanical system. As the force of the hand does work on W on the book, you can see this book gains like when you when you do the force of the hand, like when the force of the hand does work W on the book, actually the book gains gravitational potential energy. Yeah, from the low UG to the high UG. That makes sense to you? Yeah, and actually the delta UG should equal the force of the hand does work. Yeah, W. As the force of the hand does work W by compressing the spring. Yeah, this is the other example, like the how the conservation of energy work. Yeah, as the force of the hand does work W by compressing the spring. You can see, yeah, if you compress the spring gains elastic potential energy US. Yeah, another kind of potential energy. Actually, the like a change, this change, like the changed elastic potential energy, delta US should equal W. Yeah, that makes sense to you. Yeah, this is an example of conservation of energy. Okay, and a charge Q is rebelled by stationary source charges. Yeah, a hand must push on the charge Q in order to move it closer to the source charges. Yeah, you can see here there are some source charges. Yeah, and a charge Q. This charge Q is positive. It's repelled by these source charges, because yeah, you can see those source charges is positive, and this charge is also positive, so it will have a force like this, push the charge away, and a hand must push on the charge Q in order to move it closer to the source charges. Yeah, the hand does work transferring energy into the system of charges. That makes sense to you. And you can see the difference of and like electric and electric potential energy change. You call this work. The hand does work. Yeah. The charge Q gains the electric potential energy. Yeah. That makes sense to you. Okay. Yeah, actually it's similar with the spring, it's similar with this book. Yeah, it's just like the force is different. This force is electric force, not like yeah, like the spring force, not like the gravity force. Yeah, the energy is electric potential energy. We just represented the electric potential energy using this symbol. And we can determine the electric potential energy of a charge when it's at a particular position by computing how much work it took to move the charge to that position. Yeah, you can see the charge. We can determine the electric potential energy of a charge when it's at a particular position. For example, here. Yeah, by computing how much work it took to move the charge to this position. Yeah, like yeah, this is like how can we determine the electric potential energy in our charge? Yeah, we will talk more details later. Yeah, before we talk more, and let us like review some quick chat questions. In physics, what is meant by the term work? Yeah, I think you have already learned this before. Yeah, actually, according to the definition of work, it is energy transferred into a system by pushing on it. Yeah, this is the work. You can see it. For this example, and for this example, example, yeah, it is always the energy transferred into a system by pushing on it. That makes sense here. Okay, yeah, the right answer should C. And let's check the other one. As a position charge is moved from position I to position F, is its change in electric potential energy positive, negative, or zero? Firstly, let's draw some important point. Yeah, a positive charge, which means like there will be a positive charge is moved from position I to I. Is its change in electric potential energy like a positive, negative, or zero? you can see from here, for the question 1, from I to F, you can see actually this distance is the same thing. Yeah, if there is there is another positive charge. If one positive charge from here to here, actually there is no change to for the electric potential energy. You can see, am I right? Because here and here, it is the same situation because this distance is the same thing. So it should be 0. Yeah, and for this one, yeah. For the second one, you can see like if you push, you move a positive charge from I to F, which means the electrical potential it decrease. Yeah, and correspondingly, the electrical potential energy will also will be negative. Yeah, so it should be this one. And let's check the third one, which means if you move a positive charge from I to F, which means you are away from a negative source, which means the potential energy should be positive. Yeah, so this one. And actually, for the 4 and 2 is a similar thing. And you move it from I to F, which means you get away from like the positive charge source, which means the electrical potential energy should be negative. Yeah, so it will be negative. So the right answer should be B. Yeah, that makes sense to you? Yeah. If you have any question, just let me know. Okay, and then let's continue. Yeah. In the electric field model, source charges alter the space around them, creating an electric field. Yeah, this is what we have learned in last class. Yeah, in the electric field model, source charges alter the space around them, creating an electric field. This electrical field, now the source charges themselves, exerts a force. Yeah, this force on charge Q. Yeah. Yeah, this is the equation we have learned in last class. If there is a electrical field QE, and if there is a charge Q on this field, and there will be a electric force, you can use this equation to calculate. The electric field is present whether or not a charge Q is present to experience it. Yeah, this is also we talk about in last class. The electric field is present. It's always there because there is a source charges here. Yeah, no matter this P is this charge this charge Q is now there or not out there. Yeah, the electric field is always there. Yeah, we can apply similar reasoning to electrical potential energy. Yeah, we can. Yeah, there are the similar features, similar characteristics for the electrical potential energy. Okay, to better understand the electric potential energy, we take a charge Q equal 10 NC and set the electrical potential energy equals 0 at point A. Yeah, here there is a charge Q, and the electric potential energy equals 0 at this point. And to find Q's electric potential energy at any other point, yeah, for example Q or C, B or C, we must measure the amount of work it takes to move the charge from point A to that other point. Does that make sense to you? Yeah. If we want to find the Q's electric potential energy at any other point, we must measure the amount of work it takes to move the charge from point A to the other point. Okay. Yeah, in this example, it takes a hand charge 4 mu g. Yeah, this is the unit for potential energy, electrical potential energy. Yeah, to work to move the Q from point A to point B. This is point B. This is point A. Yeah. Thus, its electrical potential energy at B should be 4Qg because the different here is 0. Yeah, we know that. And from A to B, and you do a 4 mu g work. So which means the uh, the electrical potential energy at B should be 4 mu g. That makes sense to you. Similarly, yeah, you can see here if we push it from A to C, here is C, and you do a 6 mu g work. So which means the electrical potential energy is 6 mu g. Yeah. And if we were to have a charge Q equal 20 NC here, yeah, we just initially it is 10 NCM, right? And now if we were to have a charge Q 20 NC, then according to Coulomb's law, the electrical force on the charge would be twice that of charge with Q equal 10 NC. A hand would have to do twice as much work to move the charge. Yeah, that makes sense to you. Yeah. Do you remember Coulomb's law? Yeah. Let's try to review it. Try to think about that. Yeah, actually, we know like the Coulomb's law is F force equal K Q Q dot R square, and then equal Q dot E. Yeah, this is just this Q. Yeah, you can Q here. Yeah, so which means yeah, the E, the electrical field in a specific area is a fixed thing. So which means if the charge twice and the force will test twice, that makes sense to you. Yeah, the electrical force on the charge will be twice that of a charge with Q equal 10. Yeah, that makes sense to you. Yeah. Okay. A hand would have to do twice as much work to move the charge. Yeah. A charged particle's potential energy is proportional to its charge. Yeah, from this example, we can get this conclusion. Yeah, a charged particle's potential energy is proportional to its charge. Yeah, and then if the electrical potential energy for a charge Q equal 10 NC is 4 mu g at a given point, the electrical potential energy is 8 for charge Q equal 20 because it will be like twice at the same point, and 2 mu g, and for the fab, yeah, because 10 is 4, so 2 is 4 fab. You can see if you use the electrical potential energy divide the charge, yeah, you will see all three ratios are the same. 400, yeah, okay. The expression for the electrical potential energy that any charge Q would have if placed at the same point is, yeah, any charge would have if placed at the same point, yeah, and this is the number is associated with point B, and this part is depends on the charge we place at B. Yeah, this is just this example here. This is an example because we just like said if it takes the hand charge for mu g of work to move Q from A to B, and then this is the condition. Yeah, so for this example, yeah, we have this equation. Yeah, but maybe for other example, this value will be changed. Does that make sense to you? Okay. The electrical potential V is a potential for creating an electrical potential energy. if a charge is placed at a given point. Yeah, so we can use this equation to define the relationship between electrical potential energy and electrical potential and the charge. Yeah, the relationship between electrical potential and electrical potential energy. Yeah, the electric field tells us how a source will exert a force on Q. Yeah, this is what we talk about in last class. Yeah, and the electrical potential tells us how the source chain charges would provide Q with potential energy. The unit of potential energy, yeah, like last class we know like the electrical field tells us how a source will exert a force on Q. And this class, like we talk about electrical potential. Yeah, electrical potential just tell us how the source charges will provide Q with potential energy. Yeah, the unit of potential energy is joule per coulomb or volt. Yeah, 1 volt equal, yeah, we can short volt as V equal 1 joule per C. Yeah, that makes sense too. Yeah, this. There are some like there is a class video for electric potential. You can review it. Okay. Notice the similarity of electric potential energy to this is like actually this is Colombian's law, Colombia's law. Yeah, actually we know like here. We just talk about it. Yeah, it's just this is Colombian law. Yeah, and then we write the equation U electric equal what? Equal VQ. Am I right? Or QV if it is obvious. If you want to compare with each other, QV. Yeah, and you can see the similarity of electrical potential energy with this Colombia's law. This is for the electrical force, and this is the electrical potential energy. You can see it has similarity. Like the electrical field, electrical potential is present at all points in space. Yeah, you can see there are like charge sources. So like electrical potential is present at all points in those space. Yeah, the electrical potential is there whether or not a charge Q is present to experience it. Yeah, you can see here is Q, here is Q, here is Q. No matter this Q exists, and potential electric potential is always there because because there are some like sources charge sources. Yeah, that makes sense here. Okay. Yeah, let's view some quick check questions. Yeah, two charges are brought separately into the vicinity of a fixed charge, positive Q. Yeah, this is the fixed source charge, positive Q. Firstly, like a positive Q, small q, yeah, is brought to point A, yeah, a distance r away. And second, like a positive small q is removed, and negative small q is brought to the same position, same point A. Yeah, so the electric potential at A is like greater for the q charge in situation A and 1, or greater for the negative Q charging situation 2, or same for both. Yeah, actually this question is easy. It should be the same for both, because we know like the potential energy, the electrical potential is always there. Actually, it's depend on the fixed source charge. It will not like depend on the like this Q. Yeah, just pay attention here. The potential, electrical potential is one thing. Here, this equation is for electrical potential energy. Yeah, so electrical potential and electrical potential energy is two things. Just don't mix them up. Yeah. So because the electrical potential is only depends on like a fixed source charge. So actually in point A, the potential electrical potential is the same thing. Okay. Actually, you can see. Oh yeah, the answer is C. And there is another question, and yeah, you can see it's similar to that one. The two charges are brought separately into the vicinity of a fixed charge, positive capital Q. First, the positive Q is brought to point A, a distance r away. Second, like positive Q is removed and negative Q is brought to the same point A. Actually, the difference between this one and that one is just that the question is different. The electric potential energy at point A here, it just asks you electric potential energy. The next one is ask you electric potential. Yeah, so just pay attention to that. Yeah, so which one is right? Greater for the QA charge in situation A1, or greater for the negative charge in situation 2, or the same for both? Yeah, actually you can see, we know like mm, the like the equation for the electrical potential energy is U equal what? Equal Q V, am I right? Yeah, V is potential, yeah, electric potential. Here, the electric potential is same here, am I right? And so the difference is like the Q actually is A, because this one is positive, this is negative. Yeah, that makes sense to you? Yeah, the positive is it's like the potential electrical potential energy will be greater for the will be greater, yeah, than the negative charge. Yeah, does it make sense to you? Okay, let's continue. Yeah, yeah, there are some like typical electric potentials. Yeah, brain activity at scale. Yeah, EEG usually is approximate potential is 10 to 100 millivolt. Yeah, the cells in human body is 100 like a mini microvolt, and battery is 1 to 10 volt, and the household electricity is 100 usually, and the static electricity is 10 k volt, and the transmission length is 1000 k volt. Yeah, it's huge, am I right? Yeah, so let's check one example problem. Finding the charge in a finding the change. So finding the change in your charge's electric potential energy. A 15 NC charged particle moves from point A, where the electric potential is 300 volt, to point B. Yeah, where the electrical potential is negative 200, which means the difference should be 300 plus 200, it is 500. Yeah, because from 300 volt to negative 200, it is 500, am I right? By how much does the electrical potential change? By how much does the particle's electric potential energy change? And how would your answer differ if the particles charge were negative 12, negative 50 NC? Yeah, the charge in electrical potential delta volt is the potential at the final point B minus the potential at the initial point A. Yeah, from equation 21.20, 21.1, we can find the change in the electrical potential energy by noting that actually this equation is just U electric equal QV. Yeah. So the difference electric potential energy is equal the potential energy electric potential energy in point B minus potential electric potential energy in point A is equal this one QVB minus VA with Q delta volt. Yeah, we know the delta volt time, right? And we also know the Q. So we know the delta volt equal negative A because it is from A to B. So you need to use like a B minus A. So it is negative 500. Yeah, this change is independent of the charge Q because electric potential is created by source charges. Yeah, we talk about that. Yeah, the change in potential electric like particles electric potential energy is yeah, using this equation it is 50 mu 50 nc, right? And then multiple the negative and it is negative 7.5 mu g. Yeah, a negative NC charge would you have? Yeah, you will have because you just change it to negative. Yeah, it is positive. I think it equal. Yeah, it's equal symbol here. Equal 5.5 7.5 μg because Q charge then while delta volt remain unchanged. Yeah, changes then while delta remain unchanged. Yeah. Let's assess this problem. Because the electric potential at B is lower than that at A, the positive charge will lose electric potential energy, while the negative charge will gain the energy. So which means why this one is negative? Yeah, because it will lose energy, and this one is positive because it will gain energy. That makes sense to you? Okay. Let's talk about the sources of electric potential. Yeah, like firstly, let's think about one question: how is an electric potential created? Yeah, if there is no force on charge Q, no work is required to move it from A to B. That makes sense to you? Yeah, charge Q's electric potential energy remains unchanged as it is moved from A to B. So the electric potential energy B equal A. Yeah, because if there is no force on charge A, yeah, so there is no work is required to move it from A to B. That makes sense to you? Yeah, because there is no other force. Yeah, charge Q's electric potential energy remains unchanged as it moved from A to B. So for this situation, the electric potential energy at A equal at B. Yeah. Because the electrical potential energy equal this QV, so it must be the case that VB equal V because Q is the same Q. We see that the potential difference delta also here delta V equal V voltage voltage B minus voltage A. Yeah, V minus B is 0. Yeah, that makes sense to you. Okay, there is a video, you can also check it. Okay, and if electrons were transferred from the right side of a capacitor to the left side of a capacitor, the capacitor would have no net charge, but the charge would be separated. Yeah, you can see here the capacitor still has no net charge. Yeah, but charge you can see because here all the negative is here, all the positive is here. So the net so here in during these things the net charge will be 0. Yeah, so but the charge has been separated to given the plate charge positive Q and negative Q. Now because Q is repelled from the positive plate and attract to the negative plate, the hand must do work on Q to push it from A, here is A, B, from A to B. So there must be an electrical potential difference, delta voltage between A and B. Yeah, does it make sense to you? Yeah, because even there is no light charge, yeah, but the charge, because Q is repelled from the positive plate, yeah. So the hand must be do the work to push it from A to B. So there must be an electric potential difference, delta voltage, delta V between A and B. Yeah, a potential difference is created by separating positive charge from negative charge. Yeah, that's why the potential difference come out. Yeah, yeah, because yeah, because the actually a potential difference is created by separating positive charge from negative charge. Yeah, this is like let's recall the battery. Yeah, battery, there is negative polar, there is positive polar because it is separated, and then it has a potential difference, and it is sometimes it's 5 volt, sometimes it's 1.5 volt. That makes sense to you? Okay. And let's review a quick check question. Yeah, metal wires are attached to the terminals of a 3-volt battery. Yeah, there's a 3-volt battery. What is the potential difference between points A and point 1 and points 1 and 2? Yeah, actually you can see here there is a circuit. Yeah, but it's disconnect. So because there is a metal wire, so actually here this one is just similar with this one, and this one is just similar with this one. Yeah. So which means yeah, the potential difference should 3 volt. That makes sense to you? Yeah. Yeah, you can see every point on this conductor is at the same potential as the positive terminal of the battery. Yeah, yeah, every point on this conductor is at the same potential as the negative terminal of the battery. So, which means, yeah, this one compared this one, the difference should be 3 volt. Okay, let's check the other one. Metal spheres 1 and 2 are connected by a metal wire. What quantities do sphere 1 and 2 have in common? Yeah, A, the same potential, B, the same electrical field, C, the same charge. Yeah, actually, you can see, yeah, since like they are connected with each other, so it should have the same potential. Yeah, that makes sense to you. Yeah, but you cannot sure if it is the same electric field because it has a distance. You don't distance. You don't know the specific situation. Same charge. Yeah, we don't know that. Yeah. Okay. So the answer should be C, same potential, because it's connected by a metal wire. Okay. Let's continue. Yeah. Let's continue talking about sources of electric potential. Yeah, when you shuffle your feet across the carpet, yeah, you pick up charge from the floor. There is a potential difference between your body and yeah, see a nearby door knob. The potential difference can be 10,000 volt or more, enough to create a spark as the excess charge moves from higher to lower potential. Yeah, amazing, am I right? So, yeah, in the swirling ash cloud over a volcano, collisions between large and small particles transfer charges. Yeah, gases rushing upward loft the negatively charged small particles higher than the positively charged large particles. This creates a charge separate. Create a charge separation between the top and the bottom of the ash like cloud. Actually, you can see the negatively charged small hair, it will goes here, and the positive charge large particle is here, it will be here. So this creates a large separation between the top and the bottom of the ash cloud, and the resulting potential difference can lead to dramatic lightning strikes between the top and the bottom of the ash cloud. You can see there are so many lightnings here. The same thing happens in storm cloud. Yeah, when in the summer you can see many like storm clouds. Actually, it's a similar thing. Yeah, and the lightly charged small particles will higher, and the positive charged large particle will lower, and it will create a charge separation, and then it will like have a potential difference. Yeah, and then the lightning strikes happen. Yeah, that makes sense to you. Okay. A battery uses chemical reactions to create internal charge separation. Yeah, this separation proceeds until a characteristic potential difference about 1.5 volt for a standard alkaline battery appears between the two terminals of a battery. Yeah, actually the battery, yeah, they just use chemical reaction to create an internal charge separation. Yeah, different kinds of batteries maintain different potential differences between their terminals. Yeah, but all maybe different batteries, yeah, have different technologies to create it as a potential difference. But all the batteries is needed to create this potential difference. Yeah, that makes sense to you. Okay. And in nerve, and yeah, there is another like application. Yeah, the nerve and muscle cells in your body active process create a potential difference across the cell membrane of about 17 volt. A pseudo potassium exchange pump continuously pumps sodium ions out of the cell, and potassium ions into the cell. During one pump cycle, there is a net transfer of one positive charge out of the cell, causing a charge separation. Yeah, this is like why how our body has a potential difference, yeah, across all the cell membrane, about 17 m volt. Yeah, you can see because of the sodium potassium exchange pump. Yeah, and then the uh the like sodium ions out of the cell, and the potassium ions into the cell. Yeah, this will like create a potential difference. Yeah, that makes sense to you. Okay, and actually, this is sources of electrical potential. Like how can how like electrical potential come out, because there is like a separate there is a like a charge separation. Yeah, the charge separation creates the electrical potential. Okay, let's talk about the mirroring electrical potential. Yeah, there are many practical reasons to measure potential difference. The potential at a given point depends on where we choose V to be zero, but the difference is independent of any choices. Yeah, the potential differences is what is measured. A voltmeter, the basic instrument for measure potential differences, always have two inputs, so we can measure the differences between the two probes. Actually, I think most of your house of your home has like a voltmeter. Yeah, actually, this voltmeter like it can measure the electric potential. Yeah. And this image is a macrography. In this image, a macrography of a nerve cell whose membrane potential is being measured. Yeah, a small glass. Yes, there is a small glass pipette filled with conductive fluid is inserted through the cell's membrane, and the second probe is immersed in the conducting fluid that surrounds the cell. Yeah. And you can see this micropipette can measure the electrical potential in for a nerve cell. Yeah, and is high voltage dangerous? Yeah, how can 120 volt of a household electric outlet produces a shock that is definitely painful and possible fatal when the potential difference of 10,000 volt when you scarf your feet on the capillary is not. Yeah, actually it is dangerous. It is the quantity of charge transfer that determines the physiological effect of a shock. The potential difference produced when you scarf your feet on the capillary is large, but the total amount of charge transferred when you touch a door knob is quite small. Yeah, the voltage of electric. So when you accidentally by accident you like touch some high volt electric, yeah, you just like touch the door knob, that will help you to resolve this avoid this dangerous situation. The voltage of electric outlets is much smaller, but the charge transfer can be much greater, so just watch out those situations. Okay, let's talk about the electric potential and conservation of energy. Okay, yeah, the potential energy of a charged particle is determined by the electrical potential. Yeah, we talk about this in the beginning of this class. Yeah, although potential and potential energy are related and have similar names, they're not the same thing. Yeah, we have already talked about the electrical potential and electrical potential energy. It's totally different. Not totally different. It's not the same thing. When a positive charge Q moves from a region of high electric potential to a region of low electrical potential, its electric potential energy decreases and its kinetic energy increases. Yeah, this is a conservation of energy. Yeah. Okay. Yeah, there is a table like talk about the distinguishing electric potential and potential energy. Yeah, the electric potential is created by the source charges. The electric potential is present whether or not a charged particle is there to experience it. Yeah, the potential is measured in joule per coulomb, yeah, or volt. Yeah, actually, we can see the electric potential is depend on the source charges. It's not depend on the charge in this electrical field like that. Yeah, the electrical potential energy is interaction and energy of a charged particle with the source charges. Potential energy is measured in joule. Yeah, that makes sense to you. It's different things. Yeah, this one is like a fixed if the source charges is fixed. Yeah, and the electrical potential energy, yeah, is related to the sources, also related to the charged particles. Yeah. Okay, we can apply conservation of energy to situations with moving electric charges. If we also rule out external forces that can do work, our statement of conservation of energy becomes, yeah, the uh, Kf plus electric potential energy F equal Ki plus electric potential energy F. Yeah, the F and I. Do you know what's that? Think about that a little bit. Yeah, the F represents the final, like the I means the initial. Yeah, like the in the final situation, the kinetic energy plus the electrical potential energy equal the initial in the initial situation, the kinetic energy plus the electrical potential energy. Yeah, in terms of electric potential V, the equation is yeah, because we can use this to represent this. Yeah, so we have these equations. Yeah, this is conservation of energy for charged particle moving in an electric potential V. Okay, the motion of charges can be written, yeah, like this. Yeah, because here, from here, we know we have EF minus KI equal QVI minus QVF. Like this is delta K, and this is Q delta V negative. Yeah, because you can see here this is the initial, here this is the final, and the delta V should equal Vf minus Vi, but here is Vn minus Vf, so this is the negative. That makes sense to you? Okay, so we have this equation. Yeah, when delta K is positive, the particle speeds up as it moves from higher to lower potential. Yeah, which means the delta A is positive, which means yeah, the particle speeds up as it moves from higher to lower potential. When delta K is negative, the particle slows down in moving from lower to higher potential. Yeah, because if delta K is positive, which means the final kinetic energy is bigger. Am I right? And which means the final like electrical potential energy is lower. Yeah, because the conservation of energy. Yeah, the similar thing for when the delta K is negative. Okay, and you can see here a positive charge speed up like when delta K greater than 0 as it moves from higher to lower potential. Delta V smaller than 0, electric potential energy is transferred into kinetic energy. Yeah, that makes sense to you. Yeah, these dashed green lines are lengths of constant electric potential. The potential is 500 volt at all points on this line. Oh. And a positive charge slows down when delta K smaller than 0 as it moves from lower to higher potential. Yeah, delta V greater than 0. Kinetic energy is transformed into electric potential energy. Yeah. Okay. Let's talk about the problem solving approach, like 21.1. Yeah, how to solve the conservation of energy in charge interactions. Yeah, we use the principle of conservation of energy for electric charges in exactly the same way as we did for mechanical systems. The only difference is that we now consider electric potential energy instead of gravitational potential energy. Okay, let's check the strategy. Determine the object that is moving, how it is moving, and its charge. Think about the sign of the charge and the sign and the change in potential, and decide whether the object speeds up and slows down. Yeah, you can draw a before and after visual overview. Define symbols that will be used in the problem. List known values and identify what you are trying to find. Yeah, this is the steps for, and then you solve this problem. The mathematical representation is based on conservation of energy. This one, yeah, we have already known that. Find the electric potential at both the initial and final positions. You may need to calculate it from a known expression for the potential, such as that of a point charge. Ki and Kf are the total kinetic energy of all moving particles. Yeah, some problems may need additional conservation rules such as conservation of charge or conservation of momentum. Yeah, after solve the problem, you can access the result. Check that your result has the correct units, is reasonable and answers the question. Yeah. Okay, let's check one example. Finding the final spin of a moving proton. Yeah, a proton moves through an electric potential created by a number of source charges. Its speed is this one. At a point where the potential is this one. What will be the proton's speed a short time later when it reaches a point where the potential is this one? Yeah. Let's talk about the strategy. The proton has a positive charge and it's moving from a higher potential to a lower potential. The situation is like that, illustrated in figure like 21.7a. Yeah, you can check it in the textbook. The proton will speed up as it moves. Okay, yeah, you can see this is the picture. Yeah, the figure is a visual overview of the situation, showing the details of the initial and the final states. We are drawing a longer velocity vector at the final position because we know that the proton speeds up. The mass number proton is this. Yeah, this is a constant value. Yeah, you can see before, like the velocity is this one, and the energy potential is electric potential is this, and after that the electric potential is this one, and then we need to calculate the speed, yeah, proton speed, and from the conversation of energy gives, and we have this equation. And we know the kinetic energy, kinetic potential equal this one, and we just put it here, and this is the initial, like final potential energy, and we know this one, and also this is the initial one, and here, which we can write it as this one, yeah, you just put this one and put this one to this to here, and you get this equation, and then you just put because you want to calculate the final velocity, so you can calculate the final put the values you know to this equation, and then you got this and you got this one, and then the got this one, and then like the final like speed will equal this thing, this value. A positively charged particle speeds up as it moves from higher to lower potential. You can see this one is the initial speed, and this is the final speed. You can see it is bigger than the initial one. So a positively charged particle speeds up as it moves from higher to lower potential, analogous to a particle speed up as it slides down a hill from a higher gravitational potential energy to lower gravitational potential energy. Our final result makes sense. Makes sense to you? Yeah. Okay. Let's continue to talk about electric potential and conservation of energy. Yeah, electrical energy can be transformed into other types of energy in addition to kinetic energy. Yeah, you can see here. When a battery is connected to a light bulb, the electric potential energy is transformed into thermal energy. Yeah, making the bulb now enough to glow brightly. Yeah, this energy transformed is like this one. thermal energy change equals charge and the electric potential change. Yeah. Actually, yeah, this is a simple example, but you can see those similar example in your real life every day. Yeah, when you like open the light in your house, in your home, and then like the electric potential energy will like be transformed into thermal energy to let the bulb bright. Yeah, does it make sense to you? Okay, let's check some problem. Yeah. A positive charge moves as slow its kinetic energy increase or remains constant or decrease. Yeah, because you can see this one like moves this one and yeah, and because this is positive, it has the opposite force, so which means the speed will like slow down. Yeah, so which means the kinetic energy will decreases. It makes sense to you? Yeah, so you can see from this from this to this direction, and the electric the kinetic energy will like decrease, but the electrical potential energy will increase. Yeah. Okay. Let's check the other one. A positive and negative charge are released from vats in vacuum. They move toward each other as they do, like a positive, a positive potential energy becomes more positive. A positive potential energy becomes less positive. A negative potential energy becomes more negative. A negative potential energy becomes less negative. A positive potential energy becomes a negative potential energy. Yeah, which one is the right thing? Think about that. Yeah, actually it should be C. A negative potential energy becomes more negative. Why? Yeah, because yeah, actually we can get this answer from this equation. Yeah, actually this equation I didn't give you in this class. Yeah, this like a question is can be get you know like we know like the force for one like a charge to the other one is equal k q1 q2 r square, and you know like the u, yeah, the like electrical potential energy, it actually is defined as the work needed to bring one charge from infinity to a distance r from the other charge. So the like electric potential energy also equal like you just from negative to r, then uh, do this integrity. Yeah, so then this equation will equal k q1 q2 r. Yeah, actually you don't need to like remember how to get it. Yeah, it just like use this force to get this equation. Yeah, and you can see from this equation it is opposite sense. So the electric potential energy is negative, and you can see here the distance they move toward each other, so the distance is decrease, which means the value, the magnitude is increase. Yeah, so the answer is negative potential energy becomes more negative. Yeah, does this make sense to you? Okay, let's continue. And let's check the other one. A proton is released from rest at the dot. Afterward, the proton, yeah, this proton, which one is the right answer? Yeah, actually it is, yeah, move downward with an increasing speed, because you can see this is a proton means it is a positive charge. Am I right? Yeah, positive, and then it will like go to this way, this direction, because this direction is negative. It will be attractive to the negative one. Yeah, and then from this one to from this one to this one, and there will be increase the kinetic energy and decrease the electric potential energy. Yeah, so which means it will have a increase in speed. Yeah, it will move downward. Does it make sense to you? Okay. Let's check the other one. If a positive charge is released from rest, it moves in the direction of, yeah, which one? A stronger electrical field, or a weaker electrical field, or a higher electrical field potential, or lower electrical potential. Yeah, so actually, if it's a positive charge, yeah, it should goes to what? Actually, it should go to lower electric potential. Yeah, because yeah, a positive charge, it will like go to the negative uh, direction, negative charge. Yeah, because the negative charge has a lower electrical potential. Yeah, actually, I think that this one you can understand in this way, like because a positive charge, yeah, it always like go to the lower electrical potential. Yeah, from the you can see if you draw a circle, it always from the positive to the negative. Yeah, so it always go to the lower electrical potential. Does that make sense to you? Okay, let's check the other things like the electron volt. Yeah, an electron. Yeah, like Q equal E. Actually, I think it is negative E because electron is negative. Yeah, accelerating through a potential difference. Delta voltage equal 1 volt gains the kinetic energy. Yeah, this one. Yeah, this is the kinetic energy this electron can gain. Yeah, this is the uh, uh, charge, and this is the volt difference. So it will equal this one, and yeah, and yeah, because we just because we just uh, know this is we just from this equation to get this equation. Yeah, so this equation actually I think there some mm, yeah, and here is negative q like delta v, but here actually this one should be equal negative e, so which means there is a negative e and there is also a negative, so it will be no negative, it will be e delta v voltage. Yeah, so I think here it just miss a negative symbol, and then you can put e here, the voltage here, it will be the kinetic energy will be this. Yeah, the electron voltage volt is a unit of energy. Yeah, one electron volt equal one e. It is just this one. And 1 electron volt is the kinetic energy gained by an electron our proton as it accelerates through a potential difference of 1 volt. Yeah, remember the joule remains the SI unit of energy. You must convert EV to this one before doing most calculations. Yeah, remember this if you use this one. Okay. Yeah, actually you will be confused. Here is 1.6 and here is 1. It's different. Yeah, but you can see because this is a 10 like a power negative 19. Yeah, this one should be very, very small. So 1.6 and 1 is a similar thing. Yeah, there is no big difference. Yeah, also you can check the class video for the energy changes and energy units. Yeah, and yeah, I want to add something. And 1 electron volt, short as 1 eV, is just like a unit, but it's not SI unit. The joule, this one is a SI unit. So when you calculate, you need to transfer EV to joule to calculate. Yeah, so let's check one example. Yeah, atomic particles are often characterized by their kinetic energy in MeV. So this is a unit. Yeah. And what is spin of an 8.7 eV proton? Yeah, the kinetic energy of this particle is 8.7, but this EV, yeah, because it's MeV. M means this one. Okay, and first we convert the energy to joules. Yeah, because one EV is this one, so like this it just equal this one, so the K should be equal 1.3 at this joule. So and then we know like the kinetic energy equal what equal half mv squared. So and we know the m, right? Yeah, yeah, which means v equal this one, and then this is the m, and this we just calculate the k, so we can calculate the velocity for this like atomic particle. Yeah, that makes sense to you. Okay, let's check this one. Yeah, a proton. Wait, yeah, a proton has a spin of 3.5 multiple 10 power 5 meter per second when at a point where the potential is positive 100 volt. Later, it's at a point where the potential is negative 150 volt. What is its speed at this later point? Actually, yeah, this one is now it's not like difficult. You just use this like a delta k equal like a negative q delta v, and you can see here a proton, yeah, which means the q is e, am right, and has yeah, and you can know the delta v from here, am right, and and they ask you what's the speed at the later point. At the beginning point is this one, and this is what 2 v final square divided v initial square. So and you know this one, yeah, it is just the 100 minus is 250 volt negative. So and this is E, and you just use, you know that, you know this, and you know the initial velocity, and you also know the m is just this one. Yeah, it's the same thing, and yeah, and then you will calculate the final speed. Yeah. Okay, I will just give you the hint. I will now like calculate for you. You can calculate it by yourself. Okay, let's continue to check the problem. Two protons, one after the other, are launched from point 1 with the same speed. They follow the two trajectories showing the proton speed at point 2 and 3 are related by. Actually, you can see from 1 to 2 or to 3. Actually, the distance is the same thing. Now this distance, which means 2 and 3 has the same electric potential energy. Yeah, which means so the kinetic energy is also the same thing, which means the velocity will be same. That makes sense to you? Yeah. So yeah, the answer should B. Yeah, it's just like according to based on the electrical conservation. Okay. Okay, let's check this question. Yeah, and an electron follows a trajectory showing from point 1 to point 2. At point 2, like which one is the right answer? Yeah, actually you can see from the point 1 to point 2. Yeah, this one, this charge, this charge is a negative charge, and this is the positive source charges, which means it should be attracted with each other, but this one like moves here, which means the kinetic energy, yeah, this will be smaller, and the potential, the electric potential energy should be greater, yeah, which means the kinetic energy should be smaller, so which means the speed will be smaller, so which means V2 should be smaller than V1. Yeah, that makes sense to you. Okay, yeah, the answer should be C. Yeah, because the increasing electric potential of energy, because it become less negative. Yeah, so the decreasing like the kinetic energy. Yeah. Okay. Let's talk about how to calculate the electric potential. Yeah, like we have this equation. The electric energy, potential energy equal QV. So the electrical potential can be written this equation. That makes sense to you. You just put a Q here. Yeah, and to find the potential at a point in space, we calculate the electric potential energy of a charge Q at a point. Yeah, then we can solve to find the electric potential. Yeah, our like way is like find the potential at a point in space. We calculate the electrical energy of a charge Q. Yeah, and then we know the electrical potential energy. We know the charge, and then we know the potential, like electric potential. Yeah, from this equation. Yeah, that makes sense to you. Okay. Yeah. The parallel plate capacitor creates a uniform electric field by placing equal but opposite charges on two parallel conducting plates. Yeah, this we talk about in last class. Yeah, and finding the electric potential inside a parallel plate capacity is like finding the potential for the very important case of a uniform electric field. Yeah, the charges like positive Q or negative Q on plates are the source charges that create both the electric field and the electric potential. Yeah. Okay. Yeah. And the figure shows a cross section of a charged parallel plate capacitor with a separation of D between the plates. Yeah, this is D. And we let X equal 0 at the negative plate. Yeah, here there is an X equal 0. Let me make it clear. Yeah. Yeah, here there is an X. At the beginning it is 0. And at the negative plate, and X equal is D at the positive plate. Let electric potential energy equal 0 when a mobile charge Q is at the negative plate here. Yeah, and the charge, the potential energy at any other position X is then the amount of work necessary to move the charge from the negative plate to that position. It doesn't make sense to you? Okay. The electric field in the figure points to the left. Let's see this. Yeah, points to the left. Yeah, so the force, this is the force, equal QE of the field on the charge is also to the left. Yeah, the work to move the charge to position X equal, yes, this is the work equal force, multiple displacement. Yeah, the force is like the hand force and the displacement X. So the force also equals this is the force hand. Also like the it it has a net force in one position, and the other force is just electric force, and the electric force is using this equation to calculate it. So, which means this equation equal this one. Just put QE here and X. Consequently, the electrical potential energy when charge Q is at position X is this one. Because this one equal electrical potential energy equal this hand force. So it will equal the hand force equal this one, QEX. That makes sense to you. Okay. The electric potential of the parallel plate capacitor at position X measured from the negative plate is, this is because we have this one, and we also have the equation like V is this one, so which means is this one equal what? This one equal QEX, am I right? So Q, we just like remove it, it will equal EX. And this E is what? It's the electrical field, am I right? Electrical field in the capacitor. And we have already talked about the electric field in the capacitor. It's equal this one. You can review the class in the next class. And then this is X. So the electrical potential increases linearly from the negative plate X equals 0 to the positive plate X equals D. Because this is just the Q, it's a fixed thing when the capacitor is fixed. And this one is constant. And this one is what is it? A? Do you guys remember that? I just want to cut. The A is just the like a plate area. Do you remember that? We talked a bit about this in last class. The electrical potential in and the potential difference delta like a voltage between the two capacitor plate is this is V minus positive minus negative, equal ED. Because you can see here V equal what? EX, and positive, which means ED, and negative and E vertically 0, so which means it equals ED. This is the potential difference. That makes sense to you. Okay. And in many cases, the capacitor voltage is fixed at some value. The delta VC by connecting its plates to a battery with a known voltage. In this case, the electric field strength inside the capacitor is this one. Because delta VC equal ED. So which means the electric field equal E equal delta VC divided D. So the electric field strength inside a parallel band capacitor can be represented using this equation. This means we can establish an electric field of known strength by applying a voltage across a capacitor whose plate spacing is known. That makes sense to you? We can establish this electrical field of known strength by applying a voltage. We can apply a voltage across capacitor. Okay. And also you need to note the plate spacing. Spacing. This is the plate spacing. Okay. And the electrical potential at a position X inside a capacitor is this one. Because the all the like voltage from the negative to positive is delta VC, and right, and the other distance is D, and as the X pass, and this is the at the position X, and what's the electrical potential that makes sense to you. The potential increases linearly from V equals 0 at X equals 0 negatively to V equal delta Vx at X equal D, the positive plate. You can also check this video to see the electric potential table. Okay, let's talk about continue to talk about the electrical potential inside a parallel plate capacitor. Below are multiple graphical representations of the electrical potential inside a capacitor. You can see here is the negative plate, there is a positive plate, and as like a charge passes, this is a equipotential surface. Here is 0, here is 1.5, and here is 1.5, here is 0.5, here is 1 volt. Yeah, you can see this is a potential graphic as x increase. Yeah, this is x. X is from 0 to D. As x increase, the voltage also increase. It's a linear relationship. Yeah, this is a equipotential map. Yeah, from the negative plate to the positive plate. Yeah, this is 0. This is -5. This is 1.5. Yeah, 1.0 voltage. Yeah. And a graphing of potential various x, you can see the potential increasing from 0 volt at the negative plate to 1.5 volt at the positive plate. You can see from 0 to from 0 to 3. Yeah, and the voltage is from 0 to 1.5. Yeah. Okay, a three-dimensional view showing potential surfaces. These are mathematical surfaces, not physical surfaces. Yeah, actually, this surface does not do not exist. Yeah, it's just like a mathematical surface. Yeah, that has the same value of voltage at every point in this surface. Yeah, which means in this surface, every point is the voltage for every point is 0.5 voltage. Yeah, the equipotential surfaces of capacitor are planes parallel to the capacitor plates. The capacitor plates are also potential surface. Yeah, you can see in this surface it is 0 and in this surface it is 1.5 voltage. Okay, a two-dimensional equipotential map. The green dashed lines represent slices through the equipotential surfaces. So V has the same value everywhere along such a line. We call these lines of constant potential equipotential lines or simply equipotentials. Yeah. Okay. Let's talk about one example. A parallel plant capacitor is constructed of two discs spaced 2 mm apart. It is charged to a potential difference of 500 volt. A proton is shot through a small hole in the negative plate with a spin of this one. What is the furthest distance from the negative plate that the proton reaches? Okay, we will treat this problem using conservation of energy. As the proton moves towards a higher potential, its potential energy will increase, so the kinetic energy will decrease. We are looking for the point at which its kinetic energy has gone to 0. This is as far as the proton will go. Yeah, and this figure is a before and after visual overview of the proton in the capacitor. The equation 21.2 is an expression of conservation of energy for the situation. Do you remember what's that? It is delta K equal what? Equal K equal Q delta. What? Do you remember that? Try to. It's V. Yeah, think about that. Yeah, actually, you can also use this equation like a K initial plus QV initial equal K final plus QV final. Yeah, okay. And we set the starting point of the proton at the left plate, and we take the potential at this point to be 0. So V initial equals 0, and the potential between the plates of the capacitor is given by equation 21.8 at the final position. XF, the kinetic energy is 0, so KF equals 0. Here here is 0. Yeah, so here is 0 because velocity is 0. Okay. Okay. And we use the uniform. We use the information we've assembled to work out the terms in equation 21.2. Yeah. Yeah, this equation. Yeah, we have all talk about that. And we talk about that as the beginning, the velocity is 0, so kf, yeah, so the final velocity is 0, so the kf is 0, and this is the final, like the q is e, yeah, and this is the final, like uh, uh, like voltage. The final voltage is just D. Yeah, so we just use the final is XF divided D, because here is XF and the total is D. So we just use this equation. Yeah, actually we talked this equation before. Yeah. And then we use this equation, and this is the whole like voltage change, and also like this is the at the beginning there is no like electrical potential energy. It's just the kinetic energy, and this is the initial voltage. This is the final position is. Then you can use this one to calculate it. Yeah. Using this equation, it is 0.84 millimeter. The proton travels 0.84 millimeter, a bit less than halfway across the region between the plates. Yeah. Before stopping and reversing course. Yeah, does it make sense to you? Okay. Let's assess our result. Our final result is a position between the two plates. Yeah, because the whole plates, whole like distance is 2 millimeter. For now, it is 1.83 millimeter. So which means it is just around here. Yeah, as it must be given the problem statement. This gives us confidence in our result. Yeah. Okay. Let's talk about the synthesis. Yeah, how to like calculate, how to resolve this kind of problem. Yeah, the parallel plate capacitor, the potential and electric field. There are several related expressions for the electrical potential and field inside a parallel plate capacitor. The variables used in describing the parallel plate capacitors. Yeah, you can see here there is a potential difference between the plates. We use this symbol like delta V C, and this is the constant electric field. Yeah, this is the constant electric field, and this is the point at which the electrical potential is to be calculated. And this is the distance between the plates D, and this is the charge on the positive plate Q. And this is the distance of the point from the negative like a plate X. Yeah, from here to here. This is X. Yeah. Okay. And there are several related expressions for the electric potential and field inside a parallel plate capacitor. Three equivalent expressions for the electrical potential are related to by two expressions for the electrical field inside the capacitor. Yeah, for the potential, yeah, you can use this equation and this equation. Yeah, and yeah, because E equals this one, Q for the capacitor plate, and also you can use this one because this is like a difference between the two plate the voltage. This is just like a, how what's the position in the charge, and this is the total like a distance. Yeah, and also E equals this one. Yeah, we can get this one. and also E equal this one. Yeah, because E equal what? V divided X, am I right? So, so which means it equal this one. Yeah, that makes sense to you. Okay. Yeah, so for the potential number point change, yeah, to find the electrical potential due to a single fixed charge Q, we first find the electric potential energy when a second charge Q dot is a distance r away from Q. We find the electric potential energy by determining the work done to move Q dot from the point where electric potential energy equals 0 to a point with a distance r from Q. We choose electrical potential energy equals 0 to be a point infinitely far from Q for convenience, since it flows a point charge goes to 0 infinitely far from the charge. Yeah, this is how to calculate the potential number point change. Yeah, and we cannot determine the work with the simple expression. This one. Yeah, for a moving charge Q dot, because the force isn't constant. Yeah, you can see the force from here to here is not constant. From Coulomb's law, we know the force on Q dot gets larger as it approaches Q. Yeah, because it has a opposite force. Yeah, and an exactly calculation finds the electrical potential energy of 2 points charge is this one. Yeah, is this one. Yeah, we talk about this like just now. It's just like U electric equal negative to R and F dr. Yeah, actually you don't need to remember how to calculate. You just need to remember like if you want to calculate the find the electrical potential energy of 2 point charges, you can use these equations. Yeah. Okay. And let's check some example questions. What is the ratio VA divided VB of the electrical potential at the 2 points? You can see here. We know the this is the equation for the electrical potential energy. Yeah, U electrical potential energy equal what? Q E Q2 R. Yeah, that makes sense to you. Yeah, and here for this for A and B, and I think it's just like K is the same thing, Q1 is the same thing. Q1 is this source, and Q2 is this charge, so it's the same thing. So the difference is just R. Yeah, one is 1 and the other is 3. Yeah, so like the VB should be 1 divided 3 because it's here, and VA should be 1, so it should be 1/3. Yeah, that makes sense to you. Yeah, using this equation we have already talked about. Okay. Yeah. Yeah, potential number point charges decreases inversely with distance. Yeah, you can see from this equation, U electric equal K Q1 Q2 R. Yeah, so it is just like inversely with distance. Okay, let's talk about continue to talk about the potential number point change. In the case where Q and Q dot are opposite charges, the potential energy of the charges is negative. The Q dot accelerates toward fixed charge Q. Yeah, you can see. In this case, the Q and Q dot are opposite charges. The potential energy of the charges is negative. The Q accelerates toward fixed charge. Yeah, you can see. Because you can see it's it's easy to understand because this is negative, this is positive. They will have the attractive force. So it will when the Q dot accelerates toward fixed charge Q. Yeah, that makes sense to you. Okay. For a charge Q dot a distance r from a charge Q, the electric potential is related to the potential energy by this equation. Yeah, actually this equation we have already talked about that. Thus, the electric potential of charge Q is equal this one, because this one U is equal what? K Q dot R. Yeah, so here V equal K Q divided R. Yeah, equal this one. Yeah, because K equal this one. That makes sense to you? Yeah, so only the source appears in this expression. The source charge creates the electrical potential around it. Yeah. Oh. Yeah, this equation tells us only the source appears in the expression. The source charge creates the electrical potential around it. Yeah. Okay. Let's talk about this one. Three graphical representations of electrical potential of a positive point charge. Yeah, you can see. This is the equipotential surfaces, and this map, and this potential map. Yeah, so you can see as the distance increase, the like the potential, the electrical potential also will like decrease. Yeah, that makes sense to you. Yeah, and this, yeah, this is let's try to analyze it. Yeah, it's just similar to the like a capacitor plate, a potential of a capacitor like a plate, and this is a point change. Yeah, when the potential, when the distance increase, and the potential will electric potential will decrease, and this is just the equivalent potential surfaces. Yeah, this is the surface equivalent potential map. This is the positive charge, and this is the potential energy. This is the electric potential. Yeah. Okay, and let's check this example by calculating the potential of a point charge. What is the electric potential 1 centimeter from a 1 NC charge? What is the potential difference between a point 1 centimeter away and a second point to like a 3 centimeter away? We can use equation 21.10 to find the potential at two distance from the charge. Yeah, use this equation. Yeah, and yeah, then you can put the K, Q, R to this equation, and you can calculate the electrical potential is 900 volt voltage. We can simply calculate if it is 3 centimeter. Yeah, you can put it 3 here. It is 3 voltage. Thus, the potential difference between those 2 points is this 600 voltage. Yeah, and the final numbers are reasonable. We've noticed that there can be a potential difference of 10,000 voltage between your figure and a door knob when you rub your feet on the cabinet. When you acquire a charge of 10 of NC, this is a smaller charge, so we expect a smaller potential. Okay, let's talk about the electric potential of a charged sphere. Yeah, the electric potential outside a charged sphere is the same as electric potential outside of a point charge using this equation. Yeah, like a KQ. Yeah, this Q is just the sphere like a charge. Yeah, okay, you can use this equation to calculate it. And suppose you connect a metal sphere to a positive terminal of a battery. This will give a positive charge to the sphere, which will be distributed across the surface. The potential V0 is the potential at the surface of the sphere. It equals this one. Yeah. R is just like the because here R is equal, it's just a sphere of radius. Yeah, the charge for sphere of radius is therefore here. Yeah, because you can see Q is here, you put it here, so the Q is here. The charge for the sphere is here. The potential outside of the sphere charge to potential V0 is this one. Yeah, you can see. Yeah, here is you can see V equal Q like PR. Alright, so like yeah, let's try to. Yeah, we know like the V we know the V0 equal Q 4 pi R and the V equal what Q 4 pi small r. So which means like the V should equal this one multiple r and r. Yeah, this is V0 and which means it is equal V equal V0 R divided R. Yeah, that makes sense to you. You can use this equation to get this one. The potential decreases inversely with distance from center. Yeah. Okay. Let's try to summarize this. And there is a synthesis 21.2, the electric potential of a charged sphere. The electric potential V on or outside a charged sphere is the same as for a point charge. It depends only on the distance and the charge on the sphere. Yeah, this one. You can see it only depends on the distance and the charge on the sphere. Okay, that makes sense to you. Okay, and this is the sphere with the totally charge Q, and this is the radius of the sphere. This is potential at the surface in V0, and this is the distance from the center of the sphere R. We want to calculate V here. And then when the total charge Q on the sphere is known at this one, and when the potential V0 at the surface is known this one, yeah. Yeah, yeah, we can use this equation to calculate V0. These expressions are valid only on our outside the sphere. So like R should greater than this one. R should greater than this one should greater than R. Yeah, that makes sense to you. Okay. And let's check some examples. Yeah, what is the electric potential at the surface of the sphere? Okay, I think this one is easy because we know the V equal R divided R V0. So the V0 equal what? R divided R V. So this is 5, this is 55 and multiple 30, which will be 90 degree and 90 voltage. That makes sense to you? Yeah, the last one is the D. And also there are some example problem. A proton is fired from far away towards the nucleus of an iron atom, which we can model as a sphere containing 26 protons. The diagram of is this one. What initial speed does the proton need to just reach the surface of? Assume the nucleus remain at the rest. Actually, you just need to use these equations to calculate it. Yeah, I will not list it here. Yeah, you can do it by yourself. Yeah, and there is a ionization energy. We can model an atom as a sphere, and suppose we want to separate an electron from an atom. Removing an electron from an atom leaves a positive charge on behind. We can assume that the electron is a surface of sphere that is equal to the size of atom. It requires energy to separate these two opposite charges. Yeah, we can use this ionization energy to like separate those two opposite charges. Okay. There are there are one examples, and there is no time to talk about this one, and you just like review this example by yourself. Yeah, actually, it is a similar. You just use this equation. Yeah, those equation and yeah, those equation. Yeah, to calculate it. Yeah, it's easy to understand. Also, here are some like the electric potential of many charges. Yeah, you can see we talk about only one charge. Suppose there are many source charges Q1, Q2. The electric potential V at a point in the space is the sum of the potentials due to each charges. Yeah, it's just like use this one, but sum all the charges. Ri is the distance from charge I, Qi to the point in space where the potential is being calculated. Yeah. So suppose there are so many this is just talk about using this equation, the electric potential is a simple scalar sum which is easier to find. Yeah, there as an example, the potential map in the figure shows the potential of an electric dipole is the sum of potentials of the positive and negative charges. Yeah. Okay. There are some examples. Yeah, actually you can check this by yourself. Yeah, it's very easy. Just use the equations, just analyze it. If you have any questions, just let me know. Okay. Yeah, this is for today's class. Yeah, today's class there are so many things. So I think you need to review all these things very carefully. But just remember, there are some equations you can use to calculate the electric potentials. Okay. Bye. See you tomorrow. Yeah, we will talk about more about electric potential. Yeah.